Hi, welcome to our third year lecture in combinatorics. Today we'll talk about graph coloring, and we will start this topic by a motivating example. So suppose we have a collection of students, let's call them S1, S2 up to S5, that are taking some courses. Let's call them C1, C2. In this case, it just happened to be the same number, C5. What we want to create a schedule for these courses that has no conflict. So that means that we want to have no two courses sharing students to be at the same time. So this problem can be understood through the realm of graph coloring. And the way it works is we can create a graph whose vertices are the courses. So we create a graph. So you have C1, C2, C5, and we put an edge between any two courses if they have a common, if there's a student that takes both of those courses. So for example, if we look at course C1, that's taken by if we look at the student S1, he's taking both course 1 and course 2, so we can put an edge there. And then if we look at course 2 and course 3, that's taken by student, so you can think of it as having the student S1 in common, the student S2 in common, and so on. Okay. And now, so in this situation, for example, if we have a collection of vertices or courses that are that is independent, there are no edges between them. So for example, C1 and C3, there are no edges there. C1 and C3 can be scheduled at the same time because there are no students that take these classes. Okay, so now if we want to schedule, so in this situation, a schedule for our problem, it's the same thing as a partition of the vertices into independent sets. So if we want a schedule with the fewest number of slots, that's a partition into independent sets with the smallest number of such independent sets. So in this case, for this graph, we can actually color the, so we can color this independent set C1, C3 with color purple. Then we can do C2, C4 with yellow, and then we can have C5 with green, and then we can have a schedule with C1, C3 in the same slot, C2, C4 in the same slot, and C5 in one slot. And this schedule is not unique, that you can find other partition into 3 independent sets. And in this situation for the cycle C5, you cannot partition it into 2 independent sets. Okay. So let's write down the formal definitions of what's going on here. So as before, we have a graph, so undirected, simple graph. Coloring, or K coloring, if you want to specify the number of colors, is a function from the vertex set to a set with k elements. So no restrictions, just a coloring. Now, coloring that respects, in some sense, the edges of the graph is called proper. So a coloring is called proper. Okay, color. If for any two adjacent vertices, for any x adjacent to y, the color of x is different from the color of y. Okay, so that's a proper coloring. And then we can define the last parameter here, the chromatic number of gamma, which is the smallest k such that gamma has a proper k color. And we denote this chromatic number by chi. Chi of gamma denotes the chromatic number. Okay. So let's do some examples, how this works. So if we take a graph, gamma is consists of the graph on n vertices with no edges. So the empty graph on n vertices, let's say if this is the first example. So you're gonna have, this is, so sometimes it's denoted as the complement of kn complement. So here I have k5 complement. Then you can color all these vertices with the same color, and because you have no edges, there are no conflicts. So 1 is the smallest number of colors that you can use. So in this situation, you have chi of this graph equals 1. And this is the only graph that has chromatic number. These are the only graphs that have chromatic number 1, the one that have no edges. Now, let's see 2 examples. So let's consider graph gamma, which is bipartite, non-empty. So at least one edge. So because you have one edge, on that edge, you need to use 2 different colors. So again, the graph could be, so it's bipartite. So you need to use at least 2 colors. So that implies that the chromatic number of gamma is greater or equal to 2. But because the graph is bipartite, you have a partition of the vertex set into 2 independent sets, as drawn here. So that tells you that the chromatic number is at most 2. So what we have here is that we get that the chromatic number of this graph is 2. So you can state these results as some simple propositions. So the first example was that gamma, that the chromatic number of gamma is 1 if and only if gamma has no edges. And the chromatic number of gamma is 2 if and only if gamma is bipartite and with at least one edge. And so these 2 cases are the simplest cases, and these are the only cases in which the characterization of graphs with a given chromatic number is known. So if you move higher, there is no such theorem of chromatic number of gamma equals 3 equivalent to something easy to verify. Okay. So in general, If you know a little bit about complexity theory, this, these are the chromatic number 1 and 2. These are the easy cases. Figuring out if the chromatic number is 3 or more is these are difficult questions, computation. So now let's do some other examples. Let's say the C5 that we did earlier. Okay, so we saw earlier a coloring of it with 3 colors. Which is here. So this coloring, this picture, tells us that the chromatic number of C5 is less than or equal to 3. But now the graph C5 is not bipartite because it's a odd cycle. And because it's not bipartite, it does not have a partition into 2 independent sets. So that means that the chromatic number of C5 cannot be 2, so it's greater than 2. And these 2 things together give you that C5 equals 3. So you can try to prove by contradiction that the chromatic number of C5 also is not 2. It's the same thing. Okay, how about other graphs? Well, before we move on to studying other graphs, let's just state a bit more clearly what is the meaning of this chromatic number. So again, the definition tells us that the chromatic number of gamma is the minimum k such that there exists a function from the vertex set of gamma to the set 1 to k that is a proper coloring. Okay. So in many situations, we won't be able to find the chromatic number from one scoop. So we will either find inequalities involving the chromatic number. So if we want to prove an upper bound, if I want to prove that chromatic number of gamma is less than or equal, then say, then some number m, okay, what is this equivalent to? This is equivalent to gamma has a proper m coloring, and this is equivalent to there exists a proper m coloring of gamma. So in this situation, if you want to prove an upper bound, to prove upper bound for chi involves either construct coloring, a proper coloring, or show that one exists. We'll see that when we talk about probabilistic method, sometimes you can prove that things exist without actually constructing them. And then what about lower bounds? So lower bound for chi, if you want to prove that chi of gamma is, let's say, strictly greater than lowercase m, that involves the following thing. You want to prove that there is no proper m-1 coloring of gamma. So there's no, if you restate it, there is no m-1 coloring of gamma that is proper. Okay. So these questions are a little bit like a needle in the haystack. So if you want to show that there, just this, I'll give you a simple example. If I take T as a tree on n vertices, and n is greater or equal to 2, So this is bipartite, and it has at least one edge. So chi of t is 2. Now, there are, if you have n vertices, each vertex can be colored with 2 colors. There are 2 to the n colorings of t with 2 colors. Let's say 2 colors, the favorite colors in graph theory are 1 and 2, let's say. But there are only 2 proper colorings of t with these colors 1 and 2. So from 2n, the number of all possible colorings, there are only 2 that are proper. You can do them in a breadth first set. You root the tree at one vertex, and then you color that root 1, and then the neighbors, you color them 2, the neighbors of the neighbors, you color them 1, and so on. But you can also switch the colors from 1 to 2 all over the graph. So you get 2 proper colorings out of 2 to the n such colorings. So what bounds can we find for the chromatic number of the graph? So let's look at the lower bounds. Okay, so the first one is if omega of gamma is the clique number. Well, let me do something better. If we have, if gamma prime is a subgraph of gamma, then chromatic number of gamma prime is less than or equal to the chromatic number of gamma. So the way you should interpret this, if inside the graph gamma, for which I want to find a lower bound, for whose chromatic number I want to find a lower bound, I have a graph whose chromatic number I know, then I can always have this inequality. And the proof is easy because any proper coloring of gamma using chi of gamma colors is a proper coloring of gamma prime. So, okay. Now, what consequence do we have? So one immediate consequence is the following, that if omega gamma is the clique number of gamma, so this is defined as the largest number of vertices in a complete graph, in a complete subgraph of gamma, then omega of gamma is less than or equal than chi of gamma. And again, the proof follows from 1 because there exists a gamma prime subgraph of gamma such that gamma prime is the same thing as the complete graph on omega gamma vertices. And now the chromatic number of gamma prime is the chromatic number of this complete subgraph, which is the number of vertices. Okay, so let's say if you have a graph like this, from the picture, you can tell that we have a complete graph here on 4 vertices. That's a K4. So that implies that the chromatic number of the big graph, let's call it gamma, is greater or equal than chi of K4, which is 4. Now we'll discuss this in a little bit, but you should know that there are graphs where chi of gamma is bigger than omega of gamma. So we already saw one example, the cycle C5. So the chromatic number of C5 equals 3, but that's bigger than 2 because this graph has no triangles. And we'll prove in a second the result of a Polish mathematician, Mycielski from 1955, that showed that for any k greater or equal to 3, how to construct graphs with chromatic number, let's say graphs gamma k with chromatic number gamma k equals k, and omega of gamma k equals 2. So the smallest as you can be means no triangles. So this was later generalized by Erdős and Renyi, but I'll mention this a bit later. Okay, we'll go into the details a bit later. One other lower bound is in terms of the independence number of the graph. And so what is the independence number of a graph? So alpha of gamma denotes the independence number of gamma. And this is defined as the largest number of vertices in an independent set of gamma. And as you recall, an independent set is a set of vertices that induces no edges. So there are no edges between any vertices in the independent set. So now what happens is that when you do a proper coloring, so let's say gamma has a proper K coloring, say K is the chromatic number of gamma, the smallest number of colors, okay? What does that mean? That means that we can look at the vertices, vertices V1 are all vertices X such that X has color 1, and it can go all the way to VK. Now vertices X has color K. Okay, so now what happens here is that these are called color classes of this coloring. And because our coloring is proper, what we have is that V1, VK are independent sets. Independent sets that partition the vertex set. So I think that's clear. And so what do we get? Well, we get that the cardinality of V is the sum of these cardinalities, V1 plus VK. But now for us, alpha of gamma is the largest size of an independent set, and all of them are all of these VJs are independent sets. So this is less than or equal than alpha of gamma plus alpha of gamma for all of them. And how many of them are K times alpha of gamma. And that's the same thing as chi of gamma, alpha of gamma. So if you unpack this, it gives us the following result, that the chromatic number of gamma is greater or equal than the number of vertices in gamma divided by alpha of gamma. And since the chromatic number has to be an integer, you can rephrase it as, you can also rewrite it as chromatic number of gamma is greater or equal than the ceiling of the number of vertices in gamma divided by alpha of gamma. So that's the same. So in our previous example, with the cycle C5, number of vertices is 5. What is the independence number of this graph? So the largest number of vertices such that no two of them are adjacent. So you can find this by following procedure. Let's say we pick one vertex in this independent set. How big can, how large of an independent set can we construct? Well, if we pick that vertex, then its two neighbors are off limits because they cannot be in any independent set. And then if we try to add one more, then we can only add one more because then this one is off limits. So it's easy to see that alpha equals 2. And in this situation, you have that the number of vertices divided by alpha of C5 is 5 over 2. And you get that the chromatic number of C5 is greater or equal than the ceiling of 2.5, which is 3. So that matches the upper bound from the construction. Okay, so I mean, sometimes this bound can be good. In this situation, you can kind of get a feeling when this bound will be good. It will be when there is a proper coloring with K colors, K being the chromatic number, in which the color classes have sizes very close to the independence number of the graph. Okay, let's try another example. Let's try the Peterson graph. So the Peterson graph, what's the chromatic number? So you start, okay, it has to be at least 2 because we have edges. Is this bipartite? So bipartite, we have to look for odd cycles, and there are odd cycles. There's a 5 cycle around. So it's easy to see that the chromatic number of the Peterson graph is greater or equal to 3. Now, you can, let's, don't worry about upper bounds for now, but what about this upper bound with the independence number? So the number of vertices is 10. What's the independence number of the Peterson graph? Well, you can try to do a similar argument, and it kind of works. You can pick a vertex here in the independent set, and the neighbors are off limits. And then I can try to pick another vertex here. Neighbors are off limits. I'm left with how many vertices? With 3 vertices, and I want to have as many independent sets as possible, many vertices as possible. So the best thing for me is to pick these 2. So I end up with 4, and it turns out that the independence number is actually 4 with this graph. And here you get the same lower bound for Peterson. It's at least the floor of 10 over 4, which gives us 3. Okay. Now let's move on to upper bounds. And as I mentioned before, if you want to prove an upper bound, you can just try to determine a coloring of okay, with that many colors. One way to do it is to do what is called a greedy coloring, so upper bounds. So what we do here is we can order the vertices. So you have the graph gamma. So you order the vertices in some order, V1, V2, Vj, all the way up to Vn. And now we will use colors 1, 2, blah, 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 and so on. And we start from the left and we color Vj with the first available color so first available means the smallest that that has not been used on its neighbors in V1 blah 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 Vj minus 1. Okay, so that's an example of the greedy color. So let's try an example. Make a small graph. Okay. So this graph, let's try 1, 2, 4, 5, 6. So if you label the vertices this way, so you have, let's label 1, 2, we go in this order, 2, 3, 4, 5, 6. If we go in this order, then the first vertex is 1, so we can give it color 1. Then the second vertex is that we're coloring is 2, and 2 is not there's no problem there because we can also give it color 1. Now the third vertex is 3, and it has a conflict with vertex 2, so we can give 3 color 2. Now the fourth vertex is also in conflict with 1, so I can give 4 color 2. And then the fifth vertex, you see it's adjacent to 2 and 4, but 2 has color 1 and 4 has color 2, so the fifth vertex gets color 3. And the sixth vertex similarly gets color 3. So clearly what we get you will get this coloring with 3 colors of this graph. This graph is just cycle C6. And the coloring is proper. So my point here that these procedures produces a proper coloring. But this example, which may or may not be optimal. So it all depends on the ordering of the vertices. So there are n vertices, or there are n factorial possible ways of ordering these vertices. So in this situation, for the simple graph C6, in which you order these vertices alternating, then you see that we get a proper coloring with 3 colors, but clearly 3 is not the optimal here. However, you can get for any graph, so there's a catch-22 in this proposition. For any graph, gamma, there is an ordering. Actually, there are probably several. There is an ordering of its vertices where the greedy coloring is optimal. Okay, and how does that work? So I will show it here on the top, and I'll go back to the cycle in a bit. So if you have an optimal coloring of your graph, let's say here you have the vertices V1, vertices V2, and here you have the vertices Vk, where k is the chromatic number of gamma. Then you list the vertices, you put the vertices in V1 first, in the set V1, in any order you want. That's an independent set. So you put those vertices in V1 first, then you put the vertices in V2, and all the way Vk. So you list them according to these independent sets. And then when you run this greedy algorithm, you pick a first vertex here, you get color 1. Then the second vertex here, that's an independent set, so it gets color 1. So all the vertices in V1 get color 1. And then you move to V2. There must be edges here, because otherwise you could combine V1 and V2 together, and you can make it a bigger independent set, contradicting this minimality of K. But now, so in V2, you color these vertices here, and you get 2, 2, 2, and so on. So when you end up at the end, you get these vertices will be colored K, K, K. So you will use, at the end, you'll use K equals the chromatic of number of colors. So for our situation here, let me write it below. I can do a different ordering. I can do the ordering 1, 3, let's put a line here, 5, 2, 4, 6. And so how does it work? First, 1 gets colored with color 1, 3, also color 1, 5, color 1. And then you move to the other independent set, and each of them will get color 2, 2, 2. So this gives you chi of C6. But again, you see, this is a catch-22, because you want to use the greedy coloring to find an optimal coloring. So you know, finding this optimal ordering of the vertices, yeah, it's actually equivalent to finding an optimal coloring, and this is quite hard in general. Now, nevertheless, this greedy coloring can give us something. So from the greedy coloring, if you use that procedure, you get that the chromatic number of gamma is less than or equal than 1 plus a maximum degree of gamma. So delta of gamma is the maximum degree. Okay. And why is that? Well, you take any you take any ordering, of the vertices of gamma. And basically we claim that in the greedy coloring, using this ordering, we use at most 1 plus maximum of delta, or 1 plus delta of gamma colors. And why is that? Well, so the colors that we'll use are going to be 1 all the way up to delta, delta plus 1. That's what I claim, that these colors are sufficient. And so why is that? Well, when we end up at the vertex Vj, for example, the number of neighbors that lie before it, it's the number of neighbors that Vj has in this interval that comes before it. That number is at most the degree of Vj, which is at most delta. So even in the situation that this vertex Vj has exactly, let's call them x1, blah, 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 x delta neighbors. So even if it has x delta neighbors before, and all of them have gotten different colors, okay, all of them have gotten different colors. Because we're using, so here you could have delta such colors, but we're using delta plus 1 colors. So there's always a color that is available for Vj that won't conflict with the colors on its neighbors. So that's basically it. And there is a result of Brook's, which we're not going to prove. This is Brook's theorem that improves this result. And it says that essentially tells you when you have equality there, and equality in these inequality 2 happens if the graph is complete graph or odd cycle. So it says that if gamma is not a complete graph nor an odd cycle, then the chromatic number of gamma is at most the maximum degree of gamma. Now, this greedy coloring that we used for our upper bound can be useful, and I'll give it an example for you of a family of graphs in which this is quite useful, and that's a family of graphs called interval graphs. So greedy coloring works well on some families of graphs, say such interval graphs. So what's an interval graph? So gamma V is an interval graph if there exists a family of intervals on the real line, Ix, x in V. You can take them closed if you wish, on the real line, such that x is adjacent to y if and only if their corresponding intervals intersect. So you can think of it as some kind of timetables and so on, where you have conflicts between two intervals. Obviously if they intersect, and you can make a graph out of it. So here's an example. I think I drew this in the notes. Let's say we have this interval A, interval B, C, D, E. So I didn't put them all on the line, but you can project down if you want. And what graph do you make out of it? Well, you can make A here and B here. They're not adjacent because they're disjoint, but C here is adjacent to it. And it's also adjacent to D. C is adjacent to B, and it's adjacent to E. And then D is adjacent to G. G is adjacent to B. And same thing here, F. Okay, so this is a graph. And it turns out that if gamma is an interval graph, the chromatic number actually equals the clique number. So in this case, the clique number is 3, so the chromatic number of this graph would be 3. And how does that work? Well, lower bound, this one we knew it already, and all we have to do is to actually find a coloring, find a greedy coloring. So what you do is use greedy coloring, order the vertices or intervals according to their left endpoint, to their start. And it turns out when you do that, you can get the coloring chi of gamma is at most omega of gamma. So this requires a proof, which I won't do here, but just look here, the ordering that you will do, it would be something of the form C, F, A, D, G, B, E. So if you use this ordering, you will get a coloring with omega gamma colors. Okay. Now let me finish with the Mycielski's result. So you want to construct for any k greater or equal to 3, shows how to construct gamma k with chromatic number of gamma k is k, and gamma k clique number is 2, meaning no triangles. So it goes in, it's a recursive construction. So it works like this. For k equals 2, you can find such graph. The easiest one is the cycle C5, which I'll draw in this kind of strange fashion. And now the general procedure is as follows. So to go from k to k plus 1, what you do is the following. So I'll do this by the example of this cycle. So what you do is you take the graph, so maybe I'll do it in two parts. So you take the graph gamma k. So in my case, I take the 5 cycle. Okay. And let's denote its vertices by V1, V2, V3, V4, V5. So in general, you would have V1 over Vn. Now you make a copy of each of these vertices. So we can call it U1, U1, UN. So in this case, I will make U1, U2, U3, U4, U5. And these are kind of, U1 is the twin of V1. So you make U1, so if V1 is adjacent to V2 and V5, you make U1 also adjacent to V2 and V5. U2 is a twin of V2, so it's going to be adjacent to V1 and V3. U3 will be adjacent to the neighbors of V3, and so on. I think you get the picture. So if V1 is V1 is adjacent to something here, then U goes like that, and so on. Okay. And then one more thing we do. So we create another vertex at the end, let's call it W, and we make W adjacent to everybody else, well, all the U's. So we put here a W. Okay. So now this graph here, this is what we call the graph gamma k plus 1. And the claim is that, so we started with gamma, so this graph gamma k, so gamma k had chromatic number of gamma k, red, chromatic number of gamma k is k, and omega of gamma k is 2. The claim is that this implies that the chromatic number of gamma k plus 1 is k plus 1. And omega of k plus 1 is also 2. Okay, so I'll do sketch the proof on the example on the left. So the graph gamma k in our case C5, so there are no triangles there. So that part, we have the clique number is 2. Now, we cannot create any triangles here because we didn't put any edges. So the only place where you could possibly create a triangle is between U and the vertices in V. Now, the vertices in U, they're not adjacent to each other. So the only way you could potentially create a triangle is to pick one vertex from the U set and 2 vertices across. But a triangle there, because U is adjacent to the neighbor, let's say U1 is adjacent to the neighbors of V1, a triangle between U1 and 2 of these neighbors would mean that there is a triangle between V1 and those neighbors, and there's no such thing because of we took a graph that's not that's triangle free. So this omega equals 2 implies that gamma k plus 1 is 2. Then we have to deal with the chromatic number to show that the chromatic number strictly increases. Well, the chromatic number of gamma k plus 1 is definitely going to be greater or equal to k because we have a graph of chromatic number k in it. And then the proof is by contradiction. We assume that there is a proper K coloring of this graph gamma K plus 1, and that will force a proper coloring we can make a proper coloring on the graph gamma K using K minus 1 colors, and that's impossible.